Okay, warm greetings and good afternoon to one and all present here. So I welcome you all to CIT Quantum Hackathon 2022 workshop sessions sponsored by IBM Quantum as a part of Qubits Fall Fest. So I would like to quote a famous saying by Carol Burnett: "When you have a dream, you've got to grab it and never let it go." So with this, I'm extremely pleased to welcome our guest speaker, an incredibly inspirational person, Ms. Lorraine, One Quantum Africa. She is also a founder and chief operating officer of FaceTime to help expose female to as many STEM resources and opportunities as possible. So she is founding member and coordinator at Q Zimbabwe. Lorraine is also a Q Cousins coordinator at Q World, and she spends her free time volunteering at quantum workshops as an instructor or a mentor. So Lorraine is a recent graduate from Qinghai University of Technology, where she studied information technology. So Lorraine is currently a quantum developer and researcher at Stanford Computing. She was the first winner of Oxford Quantum Circuit's One Tech World Competition 2021. She has given talks at global events at places like One Quantum Africa meeting, so-called meetups, and has been featured in the Quantum Insider under Women in Quantum series. Congratulations on your achievements, and it is inspirational journey, man. So the dice is now yours, man.
Thank you very much. Good morning. I think that's the time. Thank you for the opportunity. I will start sharing my screen and we can start the session. Right, I hope my screen is visible. So thank you all for inviting me and thank you for attending. Welcome to this CIT Quantum Hackathon second session where we will be talking about quantum states and qubits. So before we begin and dive into the content we'll be covering today, I would like to start off with a quote by Richard Feynman, which says, I think I can safely say that nobody understands quantum mechanics. And why I've chosen to start with this quote is to just let you know that it's okay if you do not understand everything that we cover today. Learning is a lifelong process, so you might not understand it in today's session, but maybe in the next session you understand it. So don't give yourself a very hard time if you do not understand everything we are going to cover today. And also, this is interactive. I'm also learning quantum computing as much as you are learning, so we are learning together. So feel free to ask questions, feel free to contribute, or feel free to add something where you think maybe this could help the other participants. So you can make use of the chat or you can raise your hand. In case I miss anything in the chat, I will allow the host to maybe stop me and alert me of anything that I might have missed so that this can be interactive. So the overview of what we are going to cover today, we are going to talk about from bits to qubits. So we're going to talk about the atoms of computation. We are going to, I know information on this has been shared on the Discord server, but I will briefly cover it so that when we are running our first circuit, we'll not have a challenge, how to create your IBM account and how to log in so that it will help you throughout the talks and also throughout the hackathon. And then I'll talk about quantum bits, state vector, and representing quantum states. So we'll start with what is a bit. We're going to start with classical and get into quantum because you cannot have one without the other. They are related. So a bit is the smallest unit of information. So it can either be a 0 or a 1. So that is how the computers or whatever devices you're using to attend this workshop, that is how your computer is reading and representing the information to you. So we are going to be using Qiskit, which is a Python-based framework for quantum computing. So with atoms of computation, we'll start with splitting information into bits. Like I mentioned, that we have already explained what bits are. We can also define it as the world's simplest alphabet, because so for example, we can represent a number in bits. I know we are most familiar with representing our numbers through the string of 0 to 9, but all these digits, the 0 to 9 digits, can be represented in terms of bits. So for example, we'll start by writing a number to the power of 10, right? Let's say 8,514, just as an example. How we can break it down and write it as 8,000 plus 500 plus 10 plus 4. That is how we can represent the same number. And then we can also represent this number like in the power, like in powers of 10. So that would mean 8 times 10 to the power 3, which is 1,000, 5 times 10 to the power 2, which is 1,000, 1 times 10 to the power 1, which is 10, and 4 times 10 to the power 0, which is 1. So that is how we can also represent 8,514. And then we can also represent it as binary. So as binary, it would be now this number will be represented to a certain power of 2. So this very long binary number that we have here is 8,514. So we are now representing that number in terms of bits. So when we have n bits, they can be represented in 2n different states. So as an example, if we have 1 bit, it means it can be represented in 2 to the power 1 different states, which means it can be represented in 2 states. So what if we have 2 bits? How many different states can we represent it in? You can type your answer in the chat, and then I'll give you maybe just 10 seconds, but you can type your answer in the chat. If we have 2 bits, how many different states can we represent it in? So you can type your answer in the chat, and then, or if you want to say it, you are free to say it out loud, since this is interactive. Okay, I can't read the chat, but I'm guessing there are responses in there. So if your answer is 4 different states, then that is correct. If we have 2 bits, it means there will be 2 to the power 2, and then we get 4 different states. So we are now going to look at computation as a diagram. So whether we are using qubits or bits, we need to manipulate them in order to turn the inputs that we have into the outputs we need. So what we have on our screen is a circuit, right? A classical circuit. So we have the XOR gate and the AND gate, and then we have 2 inputs, A and B, and then 2 outputs, S and C. And then we have on our right, what we have is a quantum circuit. So the information we have on the left can also be represented, is the same information we have on the right, but it's just different representation. There we are using the circuit, we're using bits, and on the circuit on the right, we're using qubits. So this is the exact same information, just different representation. So are there any questions so far before we get into our first quantum circuit and then creating our IBM account? All right, so we can proceed. So in a circuit like the one we previously saw, we need to do 3 jobs typically. So the first thing we need is to encode the input, right? And then we do some computation to it, and then we extract our output. So I'm just going to share a different screen. Right, I hope this is also still visible. So the links have been shared on the Discord server, so you could as well look them up and just follow with that. There are also tutorials on how to do it, but I'll just briefly go through it so that in case you missed anything, it will make it easier. So you click the link or just type IBM Quantum Experience, and then you will go and create an IBM account. And then it will take you to a similar page where you have to enter the email account, the email address you want to use. I already have an account, so I'm just going to log in, but it's typically the same process. You log in and then you are taken to this. You're taken to this page when you have created your account. So there are different. I know other people ask why some pages are light. There are different themes, so I just chose a dark theme. So you get to this page, and what we are going to use, at the moment we are going to focus on the lab. So we will launch our IBM Quantum Lab. Right, so whilst that is loading, I will also share in the chat later on the links to creating your own your own account. But I've noticed on the Discord server the links have been shared. I apologize, my network seems to be lagging. But if it is lagging, you could either use the online version, or you could run it locally on your machine by following the steps that are also shared on Discord, by following those steps and then having installing IBM's Qiskit on your Jupyter notebook, and then you can use it that way. So that we do not waste time, since this is lagging, we have seen how to create our account. So I will go ahead and use my locally installed Jupyter notebook. So I hope my screen is visible. Let me just increase the size so that it's clear. I hope we can all see.
Yes, Lorraine, it is clear.
All right. So with our first quantum circuit, like I've already mentioned, we want to do three things. There are typically three things we do when in a circuit. We encode the input, we do some computation to it, then we extract the output. Like even when we saw on the classical circuit, we had the A and B, some computation being done, the XOR gate and the AND gate, and then we extract our output, which was S and C. So we start by initialization. So we import from Qiskit, we import assembly, which is a function, and then we have AER, which is a simulator from Qiskit that we'll be using. And then we also import visualization, because we're going to plot some histograms to help visualization of our information. So we'll start by creating a circuit with 8 qubits. So QC output is just a variable. You could give it any name. You could name it variable 1, output 1. Just make sure when you are using your variable names, you're consistent. I used QC output because it's easier to, it's in line with the context we are talking about. So we would write QC output is equals to quantum circuit. And in our quantum circuit, like I mentioned, we are going to be having, we have 8 qubits. So we have moved from bits and we are now at qubits. So the extraction of quantum circuit, we are going to start like from the 3 things that we mentioned that we typically done to a circuit. We are going to start with the last thing, which is extracting the output. So extraction of the output in a quantum circuit is done using an operation called measure O. So what measure O does is it's a command that is a measurement to each qubit in the circuit, right? And then it also adds some classical bits to write out the output. There, as you proceed, you also notice that there are times where you don't want to measure the whole circuit, but you just want to measure certain parts of the circuit. So it means on this part, you would write something different. You would write QC output dot measure. We have 8 qubits, so maybe you want to measure the 3rd qubit and then you would write 2. But in this case, we want to measure all the, we want to extract measurement from the whole quantum circuit. So we want to measure everything. That's why we are using this measure all command. I just wrote the second one for reference and for future use, but at this moment we are not using it. And then to draw our circuit, we will use the draw function. So it's QC dot, QC output dot draw. MPL is for matplotlib. It's for a better visualization since we are not using the IBM experience. If you are using it there, if you just write draw and then you put your brackets, it will give you a good visualization. So as I mentioned, we have 8 qubits. So it's 1, 2, 3, 4, 5, 6, 7, 8. So we start counting from 0. So this is the measurement gate. This is how it's represented in Qiskit. Are there any questions so far or additions? But so far. All right. I hope the silence is that we are understanding. Sometimes people are quiet, not because they are understanding, but because they're so confused. They don't even know what to ask. But even if that's the case, it's also okay. Quantum is learning is a life process, like I mentioned. So, you might not get it today, but in the next session, you might get it. So don't worry so much if you don't grasp everything today. So we want to plot a histogram with the counts of what our circuit representation will be like. So this is our code to do that. So we have, this is our probability. So we have 100% probability of getting 0, 0, 0, 0, 8 zeros on all our qubits. Why? In Qiskit, sort of like by default, we start in the 0 state. So it means before you apply any gate, when it's just, a qubit, it's going to be in the state 0. So when you then apply a certain gate, that's when it changes to 1 or, a different state when a certain qubit is, yes, a certain gate is applied to it. But from the word go, we will start at 0. So now we want to move to the second part, which is encoding and input, right? So here all we did, we just, created our empty circuit and we measured it and we have 0, 0, zeros because that's the default and nothing was done to our circuits anyways. So now we are going to encode an input into our circuit, the same circuit. So we are going to name it encode and we also have 8 qubits as before. and then we are going to, like, remember I said we start we start counting from 0. 0 is like there is a qubit that's represented at position 0. This is what we are using here are positions. So we have at position 0, position 1, and so on. So on the 7th, which is the last, we are going to apply an X gate. So what an X gate does, I'm not going to dive much into gates. More information on gates will be shared on the next talk, but I'm just going to talk briefly about the X gate since it's the one we are using right now, and it's going to apply. So what the X gate does is it flips the bit. Like I mentioned that we start at 0, and when we are working with qubits, it's either we have 0 or 1. So what the X gate does is when we have a 1, it flips it to 0, and when we have a 0, it flips it to 1. So that's how an X gate works. So we are going to encode and have an X gate put on the last position, like on the last qubit. So when we draw that, this is what we have. On Q7, we have the X gate. So this is how the X gate is shown on IBM Experience. So now what we are going to do is we are going to measure our circuit like we did previously. And then this is what it looks like when we have drawn the circuit with all the measurements. And then now we are going to plot the histogram to see what our output is. Now notice that here there is a difference. Now we have 1, 0, 0, 0, because this last one has been flipped. So please take note. Of course, this varies from maybe platform to platform, but with Qiskit, it's like we are reading sort of like right to left. So this is like 1, 2, 3, 4, 5, 6, 7, 8. So that's why we are seeing it as 1, 0, 0, 0, 0, not like from sort of like from left to right. So we get 1, 0, 0, 0, and all the other zeros 100% of the times. So just to give you a better understanding of what I'm talking about, I'm going to take another example. And if you have your IBM Experience account open or your Jupyter Notebook account open, and you can also practice and follow along as we go. So we are going to pick a random number. It could be your age, it could be your favorite number, it could be any number. So the random number that I've chosen is 35. And then 35 represented in binary is 1, 0, 0, 0, 1, 1, right? So we are going to use a circuit with 8 qubits, with 8 qubits also. So what we are going to do is on the first on qubit on position 0, we are going to apply an X gate. Why? We want to flip the 0 that's there so that we get a 1 there. And then on the second one, we also want to flip it because it might be, let me just write. Instead of it being a whole chain of zeros, we want to flip certain qubits so that we get this number representation. And then on the fifth one, we also want, which is this one, we are also going to apply an X gate so that we flip it. So this is what the representation will look like. Then we measure and draw. When we measure, this is how we measure, and then we draw. And then now we plot it on an histogram. Now notice we get 100, the probability with 100%, the same number we got, which is 1, these zeros are sort of like placeholders. So we get 1, 0, 0, 0, 1, 1, which is the same number we have here, which is the same 35 that we have. So that is how we would have represented it. I was just trying to show you how you can represent any number in terms of binary using a quantum circuit. Are there any questions so far, or any area you feel it's unclear or you want me to repeat before we move on to the next part? Right. I think we are so far we are together and understanding. So I'll go back to the slides. Sorry. Right, so now we are going to move to representing quantum qubits. So we make use of the block sphere. So this is just a diagram of it that I've put there for visualization. So a state vector in quantum physics, so it's used to describe the state of our system. So it can either be a complex vector, another state vector, an operator with only one column, a quantum circuit or instruction. So if the data in the circuit or the instruction, like the state vector, is constructed by assuming that all qubits are initialized to the zero state. So this is what I was talking about when I mentioned before we used the example of 35, how we have all zeros, and then now when we apply X gate, which flips the bit, when we apply it, it goes to 1. So it's initialized in the zero state, and then when we, after some manipulation, it changes the state. So I'm going to talk about also representing qubit states, right? So Dirac developed a powerful notation which is useful in quantum mechanics and also in quantum computation. So that notation is what we call the bracket notation. So there's those two brackets that we see here. And then the right part of the bracket is used to denote ket, and then this represents a vector. So we have column vectors and row vectors. So it means that 0 will be represented with this, and then 1 is represented in this manner. So we call the column vectors kets, and then the row vectors, we call them bras. So, combined, it forms what we call the bracket notation. So like I mentioned, we have the row, which is take note of the notation of how different the brackets are. I know at just a glance it looks the same, but the bracket is the side, and on the side, which is it's on the other side. So this would be the bra and ket notation as I've shown. So sorry, before I got to questions, I want to show how this is also represented when we are now in actual computation, that is with the actual programming of it. So we are going to explore qubits with Qiskit. So we have the same, we import the same things. Here we also add math, because we're going to use the square root, and we're also going to use pi. So we create a quantum circuit with 1 qubit, and then so that is why we write QC is equals to quantum circuit, so it is 1 qubit. So that's why we have 1 there. Initially, we had 8 qubits, so we wrote 8. If you want to be using 5 qubits, you just write 5 on this part. And then we are going to define the initial state as 1, as ket 1. So the initial state, we have 0 and 1. So the 0 and 1, if you notice on this part, 1 is represented as 0, 1, and then 0 is represented as 1, 0. So if on this part, if we were going to initialize our state to 0, then it means that on this part, instead of having 0 or 1, we would have 1, 0. So these are standard set of how we present 0 and how we present 1 in qubit. So we apply the initialization operation to the qubit at position 0, and then so we have QC initialized, then we initialize the state at qubit 0, then we draw it. So this is when we view our circuit, this is what it looks like. So we go ahead and run it on a simulator. So we are going to call the simulator that we, the kit, which to simulate our circuit, and then we are going to use the AER, which I've mentioned previously. And then so we go ahead and write, we want to save our state vector. And then we want to, for this part, we use it to get the result of our state vector. So we have print the out state, we are getting the result of our state vector, which will be this complex number. So take note, like this is information that you'll be using throughout the course, that 0 is represented as, actually let me use this slide. So 0, this is 1, 0, and that one is 0, 1. Like I mentioned, we have row vector and column vector. So for the for the cat 0, we would have it represented as 1, 0 as a column vector, and then 1, we have it represented as 1, 0 as a column vector also. And then when we are now representing brow 0, which is a row vector, we have it as 1, 0. And then if we are also representing 1 as brow 1, it's also a row vector, so we have it as 0, 1. So this is something you might not grasp it now, but with time you'll know it at the back of your head, because it's something that you use maybe, for example, when you're now using calculations and like complex numbers. These are some of the things you will use. And also when we are now introduced to gates and their representations and their manipulations, when you know this information, it's easier for you to understand, because there's also a sort of like matrix representation of the X gate. So if you want to calculate a certain result, you can do that mathematically when you know this information, this representation. I'm not sure if there are any questions. I'll stop sharing so that I can also check the chat, because when I'm sharing my screen like this, I can't see. But if there are any questions or an area where you feel it's unclear, we can go over it again, and then all right. Yes. Thank you, Darren, for sharing the link. Right. So far there are no questions in the chat. But yeah, if there are any questions or any areas that you want me to go over again, please let me know. This is interactive, so feel free to let me know. But that's the information I had that I wanted to share with you. If we also still have time, we could go over like the addition circuit in the Qiskit textbook. But I first want to address any questions to make sure that we are all understanding, because this information will also be used later on.
I had a question, but I am not sure if that is relevant. Like, it is related to quantum computing. It's okay. So the question is that if we have like two integers and we want to multiply them, so we can do that in classically, but can we do it using quantum computers or any algorithm?
if we have two integers and we want to multiply them, I am not certain in terms of multiplication, but like I've shown that any integer can be represented in terms of binary, and I've also shown a circuit of how you can represent any integer. In terms of multiplying the two integers with a certain circuit, I'm not sure, but I know there is addition of circuits. So maybe it will now be you'll not be multiplying using addition. You know how maybe 2 times 3 is just 2 plus 2 plus 2 3 times. So maybe it might be the case whereby you have to add those integers maybe a certain number of time. If it's 3 times 5, maybe it now just has to be a certain circuit, doing addition of that circuit to get the output, like carrying out the multiplication in a form of addition.
Okay.
Are there any other question? I'd really created time for questions because I wanted to make sure that everyone leaves satisfied and hopefully understanding the information, because from there you are going to be introduced to qubits. So at least if you know how we moved from the quantum gates. So if you know how we moved from the classical to the quantum, and then learning about quantum gates would now just be adding on to it.
Lauren, is there any references we can try it, like kind of lab exercise we can try it, or any link which will show that one?
Yeah, let me just share the links that of the where I got like of the references.
Okay.
I'm not sure about the yeah, so if I also come across other maybe labs on this, I will share, but mainly the Qiskit textbook and some articles on the internet are what I use, but I will look for more and also share just to help. I'm also available on Discord under Lorraine, Tsitsi, Majiri, in case you have questions, because maybe something is clear now, but maybe after getting more information, something is unclear. So feel free to also ask on Discord. I'm there to help throughout the whole hackathon and the whole event.
Thank you.
You're welcome. All right. Then it looks like there are no questions. I just made the presentation a bit short so that to allow time for questions. Oh, sorry, Reshma. Yes, thank you.
Okay. So, thank you for your detailed presentation, ma'am, and it was exceedingly informative. So, participants, please free to raise your hands if you have any doubts. Okay, I think we have arrived at the end of our session. So, I once again extend my gratitude to Ms. Lorraine for joining hands with us. So, I would also like to thank Dr. Manjula Gandhi ma'am for leading and supporting us throughout the process. And I think each and every one of you, thank each and every one of you for joining the sessions. So stay tuned in the Discord server for announcements and updates. So recorded videos of the session will be posted in a Discord server. As always, feel free to post your doubts and queries in our Discord server. So we are always there to help you guys out. So timings and links for further sessions have been circulated through the Discord channel. So meet you all on the next session by Raghavendra sir. So at 3:30 p.m. Thank you all.
Thank you.
Thank you.